So I plan to do a form today because it's called form lectures at some point. But still, I would just want to answer Gregor's question. So I would like to make precise. I hope I didn't mix what's happening with the gradings and what is the invariant with the conventional truths for the triply graded that you do obtain at the end of the day. So claim, I would just want to claim about the triply graded, and then we go over. So claim. So if you define P of A, Q, T of the Boole closure as let's say P tilde just for a second, the sum over I and J and K of A to the I, Q to the J, T to the K of the rank, or let's say let me do it to the dimension of H, I, J, K of the closure, sorry, of triply graded H, I, J, K. Let's say tensor with rationals. I don't want to enter discussion about what is torsion, if it's not torsion, with your Z coefficient. So let's just put Q for safety, and then define P of A, Q, T to be of a grade beta to be just P of A, Q minus 1. So I treat Q, I treat it as an internal grading, and I treat in this case A as well as an internal grading. And I'm only treating the homological degree as the one I take care as homological degree. So this is like a bi-graded characteristic. Sorry, P tilde, and of beta hat. So then you can check, and I want to check, that this P that satisfies some local relation. And by this I mean P of a positive crossing is equal to minus A, no, I already forgot, minus AQ P of this picture. So this is all oriented. So you can remove, this is just to fix the up to shift in the last theorem yesterday. I'm just telling you, I will not fix the up to shifts, but I will tell you what are the default. And P of a negative crossing, this is Q minus 1 P of this. And moreover, that's not so easy to, I mean, it's really a computation to check that. What is not so difficult is that P satisfies this skein relation, which you may recognize. And then what's missing to understand everything you need to, and of course P is invariant on Rho method 2 and Rho method 3, this I did prove. And with my choice of normalization, P of the unknot is 1 plus AQ squared divided by 1 minus Q squared. And what I claim is that you can change variables, modify with the rise or the number of strands, and get a more common normalization for what's called the Hochschild polynomial. But this invariant is equivalent to the Hochschild polynomial. No, because I have specialized T to be minus 1. You need to. And if you don't specialize T to be minus 1, then this is out of question. OK, fine. So as I said at the beginning of the lecture, this means that you did reprove that the Hochschild polynomial does exist. And it's not hard to prove that it's unique. So the unique invariant satisfying this kind of local relation. Yep. There's an A here, but there's no one. There's none here. So what? It's not on, I mean, this is what you compute is okay. So the point is that you have to remember is that I have, if you look to this horrible normalization, you will see that if you want to see it as a more standard way of thinking, you will take into account the number of strands. I don't know how familiar you are with transverse links, but I mean, if you play around with the number of strands and the rise, it's easy to adjust such that the negative stabilization is fine, or I don't remember, but one of them is fine and the other one is not at all. And somehow, since I'm playing with, the first thing you will do if you want to do the exercise that you make it normalize properly is find a way to to have a more natural normalization here. So this means that, in a nutshell, you have to double the A degree. You want the A square here, and then you want to replace A square Q square by just A square with a minus, because you want a minus here a priori. And then you have to shift by the power of A for the number of strands. So this will tell you that something is happening for the negative and positive crossing. I mean, if you come to tutorials, then I will eventually do that in the tutorials to fix this normalization. So this is just, yes? Yes. Here, yes. Sorry, that's wrong. Thank you. Yes.
Can you also say something that you commented on here last night, that for the P tilde is essentially finite?
Yeah. And so the other remark is that if you have a knot, so the last claim, okay, I want to do forms, but let's finish with that. This is not a polynomial, or even if it's called a polynomial. It's a rational function. So it's a polynomial A and Q, and you have to invert. Essentially, the only thing you have to invert is 1 minus Q square. That's the only term you do have to invert. But then what Gregor is asking is that if you take P tilde AQT of a knot, okay, let me be precise. So this is P tilde, so P bar, let's say, AQT of the given knot times P tilde of the unknot. And now this quantity. These second A's are really Q's. And always on the left. And then this is again a real polynomial in AQ. And that's only true, to my knowledge, for knots. Otherwise, you need to be careful. But this means that, in other words, if you think about, so this is not a finite sum, but it's fine. Because it's a series you control, because the only thing you are expanding is 1 over 1 minus Q square. And what's gradient dimension is this. You may remember from the early beginning of the first lecture, that's the gradient dimension of a polynomial ring in one variable. So this means this homology is not finite dimensional as a Q vector space, but at least for knots, it's not so bad, because you do control exactly where the infinite dimensionality comes from, and it's only for the unknot. All the rest is finite dimensional.
Does that lead to something about the homology HHH? I mean, this equality, does it say that the HHH is also somehow a tensor product?
Yes, it does. It's exactly that. I mean, I'm saying it on the Poincare polynomial. I'm not saying about the characteristic. I'm telling you that the Poincare polynomial does factorize as a Poincare polynomial or the unknot times something which is finite dimensional, which is exactly the, well, since I'm rational, this is exactly the same thing as saying that the triply graded homology of this knot is isomorphic to something tensor with the triply graded of the unknown. I mean, I'm just saying that as a Q vector space, if you give me, yes? Yeah, sorry. Sure. Okay. So now I would like to come back to forms. And contrary to what I did during the last two lectures, I want to motivate why I do care and why I think you should care about forms, or we should care about forms, all of us, for some sense. But so for do that, I will do a little bit of history. So I'm just I'm choosing. I'm choosing more again, like a more convenient and more standard way of normalizing. So I'm giving you the answer. I would like to rephrase this P polynomial in a way that is more convenient. So the most standard, or one of the most standard ways to rephrase things. I mean, if you look back in the literature of the 80s, and well, people have started to define this complete polynomial, there's a thousand of choice of normalization. There are some L, some M, some minus, not minus. I mean, at some points it converges more or less. And what I'm proposing here is I just tell you. And so P, just to be clear, then for this normalization, you do satisfy Riemann 1. And the most standard normalization from the unknot is just A minus 1, Q minus 1. So the previous claim was there's a way to change variables multiplied by something depending on the rise and the number of strands such that P becomes this P. I mean, and it does exactly the same amount of information. So that's a standard normalization. And what you may know, if you put A to be Q squared, what you get is the Jones polynomial. Okay, there's a unique polynomial satisfying this relationship with A equal Q squared, and this polynomial is just the Jones polynomial with a fixed choice of normalization and convention. And again, let's make some more easy things. If A is Q, which is really, really boring, P is equal to 1. And that's easy to see because if A is Q, you can convince yourself that first this becomes 1, and the constant polynomial equal to 1 does satisfy this case relation. So since it's unique, here it is. The other invariant you may care is A equal 1, and so that's the Alexander Conway, or Alexander polynomial, or Conway because you have a fix because it is not defined up to units, but usually if you say Conway, people replace Q minus Q inverse by Z. So you set A to be 1 and Q minus Q inverse to be Z, and this is a polynomial in Z, and that's people call the Alexander Conway. So again, it's a choice of things. And more generally, if A is Q to the N, so that's what people call the SLN polynomial. Okay, let's back to history. When this link homology theory started with, what were the first two things people were able to do? So one is this one. So it's meaning they were giving categorization of these theories. So let me, I don't know, I have enough room, but so here is the categorization. So Jones, well, this you heard about that this week. So this is what Slime was doing. This was Khovanov homology. this is, we didn't hear that much about the Alexander polynomial, but I mean, still, Marco mentioned it. This is HFK, well, let's say hat, so Knot Floer homology. That's categorized the Alexander polynomial, and these theories were described or constructed more or less or almost at the same times. I mean, early end of 90s and very early of 2000s. Well, here there's nothing interesting to do, but then people did this this SLN polynomial, which is due to Khovanov-Rozansky. And I'm just want to tell you why I was doing this work with forms. So back then, I mean, Floer is nice. He has a lot of geometric property. People were able to make it combinatorial using Git diagrams. Yes?
Is it A equal 1 or A equal Q?
A equal 1. And yeah, thank you. And I forgot something. You have, I mean, the value of the unknot is just a choice of normalization. So of course, if you want to send A, I mean, for all other cases, A is equal to Q to the n strictly bigger than 0, then it's fine. You can choose whatever you want. But of course, if you want the Alexander polynomial, you better choose the normalization P of the unknot to be 1, because if you send A to be 1 in this A minus A inverse Q inverse, you get 0, so the invariant you get is 0. But no, I mean A equal 1. I really mean that. Is that everything fine? So again, back to history. So Khovanov homology was nice. I mean, I hope Liam convinced you. You have this nice Barnaton picture. Everything is working fine. We do understand. We can do some computation. Rasmussen gave this very nice application for concordance and giving obstruction to sliced genus, and so on and so forth. HFK, I mean, I guess Marco convinced you that this is all nice theories which grab a lot of geometry. And then there was plenty of definition or classification of this SLN polynomial using various, even more advanced algebraic tools that I did, like matrix factorization, coherent sheaves on some algebraic varieties, category O, whatever you mean this. So. But what I was looking for, and I was I like the simplicity of the Barnaton picture, and I wanted something similar for this GLN or this SLN polynomial. I mean, no fancy use of matrix factorization or sheaves or whatever, just topology combinatorial, so something I can understand from everything from beginning to the end. So this is what I will do now. So using this form picture. So that was one motivation, and it turns out that one of the early questions people look at while defining Khovanov homology is whether it was a functor. So whether it does associate to knots, let's say a vector space, and to cobordism between knots, so surfaces, some linear maps. And it was quickly realized that this was true up to sign. So the original Khovanov homology is not functorial, it's functorial up to a default of sign. And then there was a certain number of attempts to fix this sign, and success to fix this sign. And what I believe or claim is forms are the right way to fix this sign. So this is the right way to have a link homology which is strictly functorial over integers or which field you do prefer. So that's a main advantage. Because going on, it was very important for some construction like scale lasagna to have something which is strictly functorial, not up to sign, really strictly functorial. So that was the main input. So let's call about forms. So what are forms? Forms are two-dimensional CW complex CW complex, locally looking like looking like what? So either you see something. So this is a facet. It's oriented, or everything is going to be oriented. So that's a singular vertex. So this is a Y cross interval. This is oriented, and I will tell you why. So there are three facets. One of them has an orientation which agrees with orientation with a singular locus, which is called the binding. And the two other do not coincide with orientation. There's additional data I will put in a second, and you will recognize it, I guess. Sorry? It's just a facet. I mean, it's just a plane, just a local two-dimensional disk or plane or whatever. That's that's a regular point. So every point here are regular. That's the first type of singularity I'm allowing, which is locally you see a Y cross interval, and then there's a third situation I'm going to take care is this picture. Fine, and this is oriented, and one of this is okay. So this means that I choose the orientation to agree on this one. So this means I choose this one to disagree on that one, and I agree with this one. So I mean I disagree on that one. I agree on that one. So I disagree on that one. And I agree on that one, so this means that I disagree on that one. And what's missing? This is that one. Okay. So that's the whole local picture. And I'm gluing. I mean, I don't want to make the formal definition, so you can think this thing to be embedded in the 3 space, and that's fine. But if you don't embed the form in the 3 space, then with the additional requirement, I'm just saying in Word, with the additional requirement is that I fix a cyclic ordering of the facets gluing around the binding. I mean, this is naturally given if you embed it, because it's oriented, so I can tell you which one is first, comes first, looking around that rule. And if it's not embedded, then I have to specify this rule as well, how the gluing goes. But it's easier to, I mean, and it's completely fine to just to embed the form. For most I do care about. Okay, so that's one of the piece of data. So there's an additional data, yes? Here, yes. Yes. Yes, this is right. I hope I didn't make that thing in front. Okay, now there's an additional, there will be a certain amount of definition today. And I do apologize for that, but this is life, I have to do it. So the other thing, in addition, you have a labeling. Of the facet. So what I mean a facet, I mean this 2-dimensional part. So that's the binding, so the singular vertex, and this is a facet. So I want the labeling of facets by integers, and I will gonna fix a rule. So so this means I have to specify for each facet an A. So A, B, C will be integers. Okay, and near binding, I'm requiring that the labeling of this facet goes as follows. So you have this facet which whose orientation agree with the binding. So for this, you're going to put A plus B, and for the other facet, A and B. So this is sometimes called the flow condition or the Kirchhoff condition. Okay, you have a facet which has a big labeling, I call it A plus B, and then around the binding, this labeling split into 2 pieces, A and B. And then for the singular vertex, A plus B plus C, So that's my big facet I started to play with. And then probably I do A. So this is B plus C. So this is probably B, and this is probably C, and this is probably, hopefully, A plus C. Yes. I mean, I choose to present the orientation, but you can choose the labeling, and you choose the labeling locally such that at each binding you have the sum. One of them is the sum of the two others, and from this you can recover the orientation. Non-negative integer. Sorry. Non-negative means strictly positive, right? I'm always mixing. Okay, zero is allowed. Yes, you are right. What did I do? Oh, gosh. So the bottom could be C, right?
Yeah, it can be C, and the left one will be B.
Thank you. No, that's not okay. Sorry, I will not.
Yeah, then the top one is A, and the right one is
No, I'm good.
Tell us how many choices do we actually
I mean,
have?
Yeah, I think the right one is
If it's true, everything else follows.
yes. I mean, if I mean, yes, every two.
Two, just two.
But I mean, you can do what you cannot do everything you want to, as you obviously just noticed. Because I just mixed it up. Is it fine now? No, it's not fine. Okay, let me just copy. And then we're good? Okay, let's check this arrow. This is fine. This is fine. This is fine. This is fine. Thank you, Laura. Yes. You can have 3 zeros around the binding. Yes, in principle, but zeros are useless. I mean, you're going to see in a second that I can just ignore zeros and erase them. So yes, you can, but I mean, it's like you just ignore the form. So it's like if you have a form with all facets labeled zeros, and you have the empty form, which is fine, but not very interesting. Any other questions? So that's one piece of the data. And then I want to go further with Liam's proposal to put dots, and it will be slightly more complicated in this situation. So plus decoration. Okay. And again, this is not strictly necessary. It just makes your life way more easy for what would follow. So what I can have in addition is a decoration. So a decoration will be on a facet, and there's some P, and some P is a symmetric polynomial in a variable. So the label does tell you in how many variables I'm decorating. I'm taking the decoration. So P lives on a facet with label A. This means this P could be 1. That's fine. So this is, if P is 1, this is like no decoration. And otherwise, it could be any symmetric polynomial. Okay, so this is what I call a decorated form. And the one you think, the way you would like to think about P is that in Liam's lecture, P was X, because A was 1 for everything Liam was doing. In Liam's talk, A is always 1. There's no facets with higher labeling than 1. Everything is. Of course, all these pictures include that in particular, you would have surfaces with a given label. I mean, if I have no binding, no singular points, so locally you look as a plane. So in particular, you are allowed yourself like closed genus G surface with a fixed labeling. This is fine. Okay. Good. So far, so good. So define. Okay. So now the other. So why would you care? And the point is that if you think about the picture I was drawing all the 2 previous lectures, these trivalent graphs. So fact. In the intersection of the generic of a form with a plane locally looks like what? Well, you see a graph. And locally, all the pieces of this graph look what's so-called Moy graph or webs. So it's a graph, but I mean, it does remember the labeling of the facet it comes from with the intersection. So you could have A plus B, A and B, A and B, A plus B. And of course, I'm not drawing it, but I mean, you could also see just an edge label with A. Okay, so what these forms are good for? Actually, they are the right. I mean, they are the right. They are the natural cobordism between this type of graphs. Okay, call this graph. So locally, it looks like it's a trivalent. So it is a trivalent planar oriented graph. With a labeling of age by integers, satisfying, let me just insert, satisfying this flow condition. So if A and B are entering, A plus B are going out. And then I'm somehow doing completely the wrong way because the first object to come into the literature are the graphs and the form come after. Okay, fine. Very good. Okay, so now the next claim is that form category so what are these form category objects? What are objects? Objects are what are this planar trivalent oriented graph with labeling plus condition. By condition, I mean that the labeling that satisfies this flow condition. And let me add that what you do add also, what could also happen here with intersection, you just see a circle. And you just cut, you see a little piece of cylinder, and you cut it, and you just see a circle labeled A. So this is as well included in the objects. And morphism, morphisms are forms. So sigma is a form. So basically what you think, you take a closed form, as I said before, and you take two planes, you intersect, and this gives you a cobordism from one graph to the other one, and this is fine. In particular, if gamma 0 is a circle or gamma 1 is a circle, sigma could be as well be just a surface, or just a pair of pants, or a saddle, or cap, or whatever. It's just a very natural generalization of what's happening. Now, if you so that's the category I want to play with. And what's the aim? The aim will be to construct a functor from form into, say, graded vector space. Okay. As you will see in a second, I will be more flexible than that. I will not do vector spaces, but I will free modules over a natural ring. But I mean, in principle, the aim is what? And if you remember the picture I'm using in the two previous sections to build this triply graded, I was using this picture actually. I was using, recall, so why would you do that? Recall that the picture I was using, all the previous literature was this picture of this trivalent graph. And now with my rephrasing today, this is the same as two, one, 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 one. I'm just, since I was only using labeling 2 and 1 instead of labeling 1 and 2, I was just doubling the H to recall that this should have label 2 and not any label. This is just the same meaning. So I have this complex I was drawing the first day, and which is a complex which does live in the same realm as what Liam is doing. He's taking complex over an additive closure or some topological or combinatorial defined category. So my category will not be that one. Will be that one, not just the Cobb category that Liam is using. I want it to be more rich and more general than just this Cobb category. So my category I want to play with this form. You can build complexes over the matrix of forms. And know what you would like to do, okay, is find what relation do I add in this form category to guarantee that whatever construction I want you're doing, you're going to produce a link homology theory. So how do you can check that it would be invariant on 1 master 2, 1 master 3, and 1 master 1 move? What's the condition you put there? And moreover, you want to make it somehow algebraic. So you want to go at the end of the day somewhere like in graded vector space or in abelian groups or something you can compute. I mean, this category Cobb is nice to play with, to do proofs and check things. But at some point, you always end up in an algebraic setup. So this means you apply a functor to this topological category. So this is sometimes called, I mean, we call it, so the aim to construct this thing is what's trivalent EQFT. So basically, EQFT is somewhere in the back. And so the first naive attempt to construct such a functor, which is cool, because it does work very well, in some sense. There's an easy way to construct such a functor. Let me tell you how to build such a naive functor. Okay, so naive attempt. So you take form, and you go into vector spaces as such, or abelian group. You send a graph gamma. Let's call this V tilde. Yes? Okay, sorry. Composition in the category is just gluing. If I have a form from gamma 0 to gamma 1, and another one to from gamma 1 to gamma 2, I'm glue. No, the labeling have to agree. I mean, I'm only allowed to glue if the labeling agree. I mean, if the graph gamma in the middle is just a graph with the same labeling. I mean, labeling is part of the data. I'm not allowed to change labeling in between. Thanks for the question. Other questions? Okay, so one easy way to do that is to take the home space into this form category. Sorry. From the empty into the graph gamma. And as Lime was doing, you do it over, let's say, rationals. So you take linear combination. I allow linear combination of a form from the empty into gamma. So I have my graph gamma. I'm looking to a form that bound this graph gamma, and I'm taking the vector space generated by all forms bounding my graph gamma, which is huge. This is infinite dimensional if you do nothing. And again, if you think about what's happening in Lam's lecture, you could do that with replacing here a form by cobordism. So before local relation. And you can say, fine, I'm going to define for you a functor from the category of cobordism. So objects are circles, morphisms are surfaces. How do you do that? Well, I'm sending each circles to the free vector space, the vector space generated by all surfaces with one boundary component. And linear combination of them. So that's fine. This is a functor. Why is it a functor? Because now if you have a graph gamma, so you have a form that goes from gamma 0 to gamma 1. So this, let's call this V gamma, so V tilde gamma. So let me just say in a word what does it does. So what's an element in V tilde gamma 0? It's a form from empty into gamma 0. So I compose and I glue with my form sigma from gamma 0 to gamma 1. This obviously gives me a form from empty into gamma 1. Fine, and this is all well defined. And it's and let me add it. Yeah, that's fine. Okay, but the problem with that is that all of this is infinite dimensional. And now if you again, if you think about Liam's lecture, what Liam did by moding out by this local relation is just ensuring that you take a quotient of V tilde, which is going to be finite dimensional. Okay, let's. He didn't rephrase like this, but let's put it as an exercise. So if you take Cob L, no, okay, sorry. Exercise after. I have to do something before. Sorry, I was quick in my head. Okay, so what's the strategy to make it nicer than just this infinite naive functor is to be able to give an evaluation of closed form, or in Yam sector for closed surface. I had to fix a rule which evaluates each closed surface and use a very wonderful idea which is due to Blanchet. Abeger, Masbaum, and Vogel, which is called the universal construction. I'm going to tell you about this wonderful idea, which was developed in another context of the Reshtikin-Turayev invariant of three manifolds, but I mean, which is exactly the same idea we are using here. So the idea is you want to have a better control on V tilde gamma, so you want to be able to give a quotient which is meaningful, and which will be useful to build these link homology theories. So what the idea is, find what's in the previous. Suppose so you can define an evaluation of closed form. Okay, well, what I mean an evaluation is a function, let's say brackets, from closed form into certain ring. So R is a ring. Commutative with unit. Okay, it takes a closed form and it does associate this bracket sigma an element of the ring. Omi? Okay, suppose I give me a value for each closed form. And then, of course, you can always define something like this. I mean, you can do trivial things. I mean, you can just randomly, if we were just playing with, instead of forms, you were playing with surface, I'm just telling you, give me a number for each closed surface of genus G, randomly. And that's an interesting question. And the output is they have to be more clever than that and build more interesting evaluation than just randomly choosing one. But suppose you can do that. What you can always do is you can take the quotient and then define V gamma to be this huge thing modeled out by the kernel of this form, or the radical, or whatever you want to call it. So what is this? Is you're going to say that two forms from empty into gamma are equal if by any way you close the form with an linear accommodation and you do evaluate with your evaluation, then it's going to be 0. So you define a huge equivalence relation on V tilde or gamma, and then you cross fingers that you do it the right way, and you end up with something which is controllable, more interesting, finite dimensional, and very interesting. Okay? Yes?
You mean we define an equivalence relation by reviewing?
Yes, exactly. The equivalence relation is that two forms from, so if you have for empty into gamma, so you have another one for empty, and you call it sigma and sigma prime, and this could eventually be linear combination of forms. So you say that two things are equal if by any means, by any g or any, let's say, sigma double prime, that you close and evaluate. So sigma, let me write it. It's probably better. Thank you. For any f, so f and f prime inside V gamma, let's say f and f prime are so f and f prime, so f minus f prime would be in the kernel of the pairing if for all G a homomorphism from gamma into empty f minus f prime composed with G evaluate is 0. Other questions? All right. Now here comes the exercise with for Liam lecture. We will answer eventually this afternoon. So the first thing is that Liam using the sphere relation 4 tube, and you say, and you already said that the torus is 2. So if you do that, compute I should add the torus. Thank you. So you compute the value in this quotient. So this should be, I mean, what I'm saying is that you can simplify using 4. You can always simplify any genus G surface, such to a bunch of integers and so on. Compute that.
This is in Cobb empty, like Cobb.
Yes, yes, exactly. Yeah. Sorry.
There's a cache in there.
You need empty condition, right?
Yeah, I put the boundary. I'm in four boundary points.
Yes, okay. By this I mean for closed case, yeah, with no boundary component. But I mean, but still you can use just this condition which are with no boundary condition. Then you can compute this, and then you can compute the home. So that's my evaluation. Okay, this is a number, and then compute into Cobb L the empty into a circle modulo. Okay, let's modulo this evaluation. And what I'm claiming, this is 2-dimensional. And Liam tell you how it's 2-dimensional with the delooping thing. And I'm just saying it's exactly the same thing. Okay, so what I want to do, what time is it? For the rest of the lecture is to define for you an interesting evaluation of form. So, okay, definition. So let's fix, let's say, a set of integers from 1 to n. So that's my capital N in the first lecture. And define a coloring of closed, let's be precise, a closed form sigma is a choice of subset is a choice of a subset of X for each facet such that around the binding So let me. So that's A plus B, that's B, that's A. There are two conditions. The first thing is that the card, so let's say, so coloring from the facet into P. So the part of X. So to a facet F, we associate, let's say, X of F. So this is a subset of X. I asking two things is that the cardinality of this set is equal to the label of F. Okay. For each facet, I have a label A, so I want to choose a subset of cardinality A into X. And same for B, and same for A plus B. And then the additional condition I'm requiring is that the subset here is just the union of the subset here and here. Plus condition that in this picture, sorry, XA is general XB is XA plus B. So I'm still using this flow condition. Instead of choosing an integer, I choose a subset, and I want the subset to match. So I have a subset here with cardinality A, here with cardinality B, and I want the subset which is here just to be just the disunion of these two subsets. Cardinal 1. So far, so good. Now comes an random amount observation. So I should have said that I'm calling this set of integers the pigments, because I'm coloring with pigments. So these are pigments. So for each pigment E into X, consider the facet. So okay, so sorry. Sigma is a form and C is a coloring. The facets of sigma colored by E. Okay, I have the coloring, and now I'm looking to all facets which have a fixed color. And then it is a surface. Okay, because just look to what's happening here, and I'll let you check what's happening on the vertex. If color I is here, then it either go in facet B or in facet B. So the binding doesn't count anymore. So you can just see the surface I'm describing here, just going from the big facet and floating here. Eventually it goes the other way around, but I mean it has to go either in the B facet or in the A facet. Everywhere. Yes. Yeah, go ahead.
XA and XB, what are
They are subsets of X.
So you shouldn't write colored by I. You should write where I is an element of XA. Because they are not colored by numbers. They are colored by sets.
Oh, okay. Are you happier with that? Sorry? No, I want I to be, I choose one color, I'm looking on which facet are color. Eventually this is empty. If I didn't use the color I in my coloring for color my form, then this is empty. It could be any color between 1 and n. No, I want it to be into X, not into XF. For a fixed color, for a fixed pigment, I'm looking to all the facets which do have this color. And I'm claiming this.
Nothing else?
No, it can be. I didn't say nothing else.
But that's why XF is not the set I.
XF is not, no, XF is not a set I. I'm just saying it's color. Colored.
According to your definition,
Okay.
coloring is a set.
Uh, thank you. Colored containing by color containing pigment I. Thank you.
Now we should forget about A, B, I mean the labels, and they're being replaced by colors, or that's it?
No, they're still there. There's another piece of data.
And is there a relation between the two? Or?
No, I mean, there's a constraint which is given by the fact that the colorings have cardinality, the label, plus the condition that the subsets of X do satisfy this condition, which is around here. But except from that, I mean, there's no relationship a priori. Any other?
The cardinality of XA is
A. XA is a subset of X, and yes, cardinality is the label of the facet it goes through. Okay? Maybe if I do simultaneously, an example would be better. So let's do an example at the same time. That's so-called theta form. So I have to specify what the, let me just say, so this is label 2, this is label 1, and this is label 1. These are just a label. So this is a form, and I'm not putting decoration for the moment, okay? There will be decoration after, but just ignore decoration for a second. And now I'm choosing, to choose the coloring, I have to tell you how many colors I can color with. So let's suppose N is 3. Then let's suppose 1. So X is what? X is 1, 2, 3. Okay. And now, if I want to choose a coloring, I need to choose a subset of 1, 2, 3 for each facet. For example, this is 1. Sorry, so this is 3. So this means with the flow condition, so that's a facet label 2. So 3 is, this color is entering this binding. So he has to go into the big facet. So the color 3 should show up on this facet 2. And then, I don't know, let's say 2. And then again, the color 2 has to show up in the big facet. So that's a coloring. I choose for each facet a subset of 1, 2, 3 with extra conditions that are on the binding. If I have 2 color entering, then the 2 colors go into the big facet, which is nearby the binding. In each binding, there's always a big facet, a facet with the larger labelings. So that's a coloring. Any questions? And so you can see that if I pick my pigment 2, and I'm looking to the facets which do include pigment 2, then this is just a sphere. And if you look to the facets which do include pigment 3, then this is also just a sphere. And if I look to the pigment 1, then it's empty. I don't have any facets with colored. For this color, we choose by pigment 1.
So it's actually oriented.
That's a good remark. The surface is oriented.
But are they the same or are they opposite?
Oh, you mean, okay, so the point is that this facet, the big facet is oriented like the binding. And then this facet with my convention has to go around. And then you're good. It's an oriented surface with the choice of orientation.
And the question is whether the upper sphere is the same orientation as the lower sphere.
So is
Anyway,
what do you mean by nope? I mean, if you choose a pose an infinity and you say with integral and so on, the answer is no. But you have to specify. I mean, abstractly, you're fine, but you have to embed it into the Swiss space to tell me which orientation I agree or disagree. So you have to tell me where it's pointing outside or inside. I mean, doesn't matter. I don't think so. Okay, is that okay? This is a surface always. Now, for each pair of pigment, ij, let's say I smaller than j, the facet of sigma containing pigment I or J, but not both. Okay, I'm looking to the facets now, which do have taking two pigment, and I'm asking that in each facet you see one of them, but not two, not both. And again, is a surface. Is a surface. And again, it's an oriented surface. And let me give names, and I'm just want to come to answer. So surface, this is called sigma I. Okay. Let me mention maybe sigma I is a surface. It may be disconnected. There's no reason for it to be connected. And this is a surface I will denote sigma ij. If you want another definition of sigma ij, this is the symmetric difference of sigma I and sigma j. Yes? Yes? I mean, it's orientable, sorry. And to make it orientable, you choose the orientation of one of the two pigments is given. Sorry, thank you. Okay, so this is a bicolor. So this is called a monocolor surface, and this is a bicolor surface. In addition, sigma ij is divided into region colored I and j. So if you're on this surface sigma ij, sorry, what you will see, so you do remember the facets. I mean, each piece of the surface does come from one of the facets of the form, and the facet is either color I or color j. So locally, what you see is, for instance, So if let's, oh, sorry, I should have done that. Let's do to the example here. So what is F2, 3? Well, it's a facet which do have 2 and 3. So this is a sphere, but somehow you do remember where the binding was attached. So there's a circle here that you do remember because you do remember that this facet was colored. Sorry, let me pick the color. 2 and 3. Okay. And then you have this circle subdividing. On each surface sigma ig, so each connected surface of sigma ig, you have a bunch of circles dividing your surface into region I and region J. Sorry. Now, okay, this is what I want to say. So what you see is you have circles on sigma ij. Let denote theta ij, the number of them. More in details. Okay. So that's the number of circles that you see on this surface. Yes. Sorry, sigma. Yes.
Do I understand correctly that the regions are oriented, these orientations disagree at least by?
Yes, exactly.
So it's just like this. It's always like this.
Yes, it's always like this. So the surface sigma ij is oriented, but for this you have to choose.
No. What I mean is each region is oriented. The two regions oriented, the three regions oriented, but those two orientations do not coincide.
Yes.
So of course I can change.
Yeah, they do not coincide. So if you
I need to remember this circle to.
exactly.
So it's more than a circle. It's a circle with the result.
Exactly. Fine. Very good. And now I need an additional data, which is I have my surface sigma ij, I have my circle, and then I have to remember where the big facet was. So you have the I and j entering the circle, so the I and j have to go out somewhere else in the form, which I erased by looking at sigma ij. But then there are basically two positions that then could look like. So either, so for all of this, I need all the data I have chosen. Let me just ignore all other pigments than I and j. So, yep. So if you see I and j, so here is passing my bicolor surface, because here I and j have to go out due to the rule of the coloring. So there are two possibilities. Either that, and then I need to remember as well what the orientation of the binding is in order that to make sense. Then you have two options. Either you see this, either you see that. And that's the only two possibilities. And for this, I need orientation of the binding, embedding of the form into the free space. And if you're not embedding the form in the free space, I need to, it's your question, you need to know the cyclic ordering around the binding. Otherwise, you cannot tell apart these two situations. Yes?
What's the first word?
You have, sorry, sorry, what was I was writing? I don't remember. Let's denote the number of them. There are circles. There are circles on sigma ij, okay, which are the trace of the binding. Okay, so you have these two situations that I can tell apart, and let's denote theta ij plus the number of circles which locally look like this, and theta ij minus the number of circles. So that's the number of circles will locally look like this, and that's the number of circles ij will locally look like this. So they are split into two pieces. And of course, as you can see on the example, I mean, they don't need to appear both. So they're either one type or the other type.
So in this example, what is it?
Good question. And I mistress that for this I need the ordering of course of I and j also to make sense. I need I and to be smaller than j because otherwise I cannot tell who is I and who is j, who is the bigger one or who is the smaller one. I need this additional data as well. And so in this example, that's a minus. That's a theta 2, 3 minus. Because if you go around the binding, then the 3 on your left, and the 2 is on your right. So the 3 is on the left when you go along the binding, and the 2 is on the right. So it's a minus circle. Okay. Very good. So sigma is a colored form. Then I will define sigma c depending on n. So n is the number of pigments I'm allowed to use as what? As a product of the facets x, what was it? XF from over facets. I will tell you in a minute what this is. Let's go for the most interesting part, which is a product over I less than j of xi minus xj, a characteristic of fij, no, sigma ij, sorry, sigma ij divided by 2 minus 1 to the sign. I will tell you in a second what the sign of this coloring is. So there's a sign. So let's look for it. So where does it live first? A priori, up to now, there's no reason. This is, at the moment, I'm going to tell you, it's a rational function in x1 and xn. Okay, I guess the denominator is fine. So it's xi minus xj power the characteristic of the bicolor surface divided by 2. But since it's a closed surface, this is divisible by 2. So this is a number, and sorry, an integer. And what is the top? What is the top is, so remember, what is PF? PF is a symmetric polynomial in the number of variables of the facet. So let's come back to example. It's maybe more efficient than anything else. So let me put an additional data. So that's my P. I put a P on this facet 1. So that's my coloring. I choose the coloring, and that's my P. And let's say P, so P is a symmetric polynomial in one variable because I am the facet 1. So let's say P is, I don't know, x squared. Okay? So now what is this evaluation? So remember that here n equals 3. So what it is? So I'm looking to the bicolor surface. Okay? Let's concentrate on the denominators. What is a bicolor surface? Well, it's you took two pairs of pigments and you look to the facet. So I already introduced one of them. So I have what? I have at least x2 minus x3. The characteristic of the bicolor surface, which is a sphere, divided by 2. So I just got x2 minus x3. Now let's stick to the definition. I'm taking the facet with let's pick 1, 2. So sorry.
Empty surfaces.
No, it's not empty.
Like I mean, for the others, it's 0.
No, I'm conscious. So I'm going ahead. Sorry. Wait. It's not empty. That's the main point. Let me continue. You will get your answer. But empty is a 0, yes. Now if you have 1 and 2, so you look to the facets which either do contain 1 or 2, but not both. So this means that if I take 1, 2, here I have 2, here I have 2, but not 1. So this is a bicolor surface. If you see a monocolor surface and a color which doesn't show up, the case of 1, this is a well-defined bicolor surface. It's a symmetric difference between the monocolor 2 and empty. So it's just monocolor 2. So actually, you also have a x1 minus x2. And for the same reason, you do have also x1 minus x3. Is that all right? And then what does it mean, the numerators? That I want to just to say is here you have a color 1 and you have a polynomial which is symmetric in one variable. And what does it mean? It means that you just substitute the variables by the variables labeled by the coloring. So here I'm coloring with 2. So my variable would be x2. So I'm just saying that I'm taking x2 squared. Let's maybe do it slightly more complicated. Let's suppose you have a q here. And I don't know, q. Sorry? There are decoration I put on the facet. At the beginning, I said I have a form plus decoration on the facet. Sorry? No. You have label, decoration, plus coloring. Sorry for that, but yes. It's a data of the form. The form plus a decoration. It's a part of the data. I mean, again, you can avoid it. I mean, in LIAMS, if you make the parallel with LIAM lecture, it's about to say, do you want dots or do you don't want dots? Not exactly because it's in a slightly different picture, but I mean, still, it's just a gadget at the moment that makes flexibility. So again, if Q is a symmetric polynomial in 2 variables, because this is a facet label 2, suppose it's x plus y, what I mean is, no, this facet is color 2 and 3, so replace the variable, whatever variables they do leave, with the variable x2 plus x2 and x3. And of course, you do need that it's symmetric, because otherwise you don't know how to plug the coloring of the variable x2 and x3. Okay? Other questions? Is it okay for the numerator of the thing? So the last thing I have to, yes?
You have something to the power x of sigma is over 2 in the denominator.
Sorry?
In the denominator, you have xi minus xj to the power
Yes. That's what I computed here. The product over I and j, so 1, 2, 1, 3, 2, 3, and in each case the bicolor surface is a sphere. Yes? C is just the coloring. Yep. Yes. It's 1. So if you evaluate the constant polynomial, substitute by anything, it's just 1. If I don't put the decoration, then it's just decoration by 1. Yes? That's, I'm going to say, I hope to finish to say that before the end. Yeah.
In the definition of the bracket, the xi minus xj, is that to the power of the order characteristic or multiplied by?
No, by the power of the order characteristic. I'm good. I can tell what the sign is. Very good. So sign of sigma c, sorry. So the sign does depend on the form and the coloring. It's what? So I'm just writing down the formula for I equal 1 to n I times a characteristic of the monocolor surface divided by 2 plus the sum over I less than j theta ij plus. So I hope I define all data over there. So that's the monocolor surface. I'm taking the characteristic divided by 2. I multiply by I. And I'm then counting the number of circles which are oriented in the theta ij, and I'm summing over all I and possibility I and j over. Okay, I didn't succeed so far to give a theorem, neither an open question, so I will do that, and then stop. Okay, so other definition. So what I will call sigma n is just the sum of a C coloring of this thing.
So no sigma has some p's, but no coloring.
Yes, some p's. So this is a decorated. Theorem. So sigma is a decorated form even if it doesn't look like to be. This evaluation is a symmetric polynomial in n variables. Okay, it's something that happened quite a lot in quantum topology. You sum up rational function, and at the end of the day, it's a polynomial. Individually, they are not, but globally, they are. Very good, and what you could do is that you could, what time is it? I'm late? I'm already late. Okay. So let me just give an open question, because then I didn't break the rule today. So again, do the parallel with Liam lecture. I introduce for you a way to define something like this in this setting, like give me an evaluation for each closed surface, and then you can do everything. But this is not the way that Liam was interesting thing. He said, give me local rules, sphere, tube, whatever, and then I can play with it. And now I'm not doing this. I'll give you a global rule to evaluate closed surface, but now I have no local rules which are satisfied. A priori, it's an open question. Find enough local rules to compute inductively this data. I'm going to show on Friday a certain amount of local rules which are satisfied, but it's not known a complete set of local relations, which means that you could forget about everything I was said today. I'm just giving you the local rule. You can compute with that. That's the magic of n equal 2. For n equal 2, this is true. I have an evaluation and a local rule. And starting from n equal 4, it's not known. For n equal 3, you can do something. You can still survive. But for n strictly bigger than 3, you have to play with this evaluation formula to be able to go on and finish the thing. I'm over time, so I'm stopping here.